Bipasha. I am the assistant professor for the university libraries. I work as an AI research scientist, and today I'm going to be presenting our talk, automating chapter level classification for electronic theses and dissertations. I did just notice that our author list is missing, but I just want to point it out that thanks to my authors, Bill Ingram, the associate dean at the libraries, and Edward Fox, my former PhD advisor at computer science. So, a brief introduction of why we care about ETDs. Electronic theses and dissertations, or ETDs, are long scholarly documents that are organized into chapters detailing academic research across a vast variety of academic domains. The figure on the right hand side this depicts the users of ETDs. So, apart from researchers and students and scholars who interact with such documents, we write it at the end of our degrees. We do have people at the libraries and educators at the universities who care about these documents and want to learn how the research is progressing at a university. So, our stakeholders interact with ETDs in various ways and forms. Apart from modern digital documents, which is prevalent in since I guess 2000, we do have a collection of historical theses and dissertation that has been digitized over time. So the motivation behind our research is that digital libraries that currently host ETDs, specifically the institutional repositories, they provide the metadata at the document level. But what we have seen that when users are trying to find the particular portions of interest from such large documents, it's quite difficult from the document level metadata. Thus, our goal is to provide chapter level descriptions to help users easily find and locate their specific portions of interest from these large booklet documents and thus facilitate better search and navigation. And finally, we want to add to item level descriptive metadata, as Jennifer was mentioning this morning. With one digital objects, we need more item metadata. This kind of aims to add to the solution where we add more chapter level labels to help users find their portion of interest faster. So broadly, this research is trying to make ETDs more accessible by using an AI-driven solution to automatically categorize ETD chapters. And we are doing so by performing 4 different sorts of experiments. The first one is we're trying to see how traditional machine learning classifiers perform when compared with their language model counterparts. The second, we try to see if fine-tuning a language model performs better than using their pre-trained counterparts. The third one is we are trying to measure if a multi-label classification helps solve the problem or gets better results as opposed to a multi-class classification. And finally, what are the capabilities and limitations of LLMs in predicting discipline labels for ETD chapters? So I'll go into detail when we're discussing each of the experiments further down the presentation. So in this slide, I briefly discussed the entire data flow diagram that we have. So we have those ETD long documents that we segment into chapters. From those segmented ETD chapter PDFs, we extract the text, which we then feed into our classification pipeline, which is capable of performing 3 types of classification: a single label, top 3 labels, and 2-level labels. Finally, we display this labels to our users, which is shown in a system that we have a prototype system developed, where they get to visually see the classification labels for each of the chapters. I don't want to go too much into detail, but just a high level. For the segmentation, we have a manually segmented ETD set, which is used for our classification experiments. For classification, we use the PQDT and ETDCL dataset. Both of those datasets are subsets of ETDs that has been mapped to the ProQuest academic classification system. And finally, when I talk about fine-tuning language model, we have a collection of 8,000 ETDs that has been used to fine-tune language models. So the first task was segmenting the long document into chapters. We tried a lot of automatic segmentation methods, and we realized that it lacked precision and accuracy when segmenting or finding chapters from the long documents, which is essential in our task because we are doing chapter level classification. Hence, we manually segmented subset of 244 ETDs into chapters. It has the front matter, which is everything before chapter one, each of the chapters, references, and appendix if it existed. And this has been done and verified by two different undergrad students that we had helped us in this. So it is sort of a ground truth because we made sure multiple people did verify this segmented document. For text extraction, we used a hybrid methodology. So as Pepper, the prior speaker was talking about cloud-based services. So Amazon AWS Textract is another cloud-based service that helps in OCRing. So after comparing a lot of OCR methods, we did realize that AWS Textract did perform well when extracting the text from the documents. But for our case, we needed clean text. That is also another requirement. Hence, I used a hybrid approach of object detection and AWS Textract. Both of those approaches yields bounding boxes. Now, AWS Textract will give me a bounding box for each of the lines and words for that page, but our object detection model trained on YOLO v7 um, is capable of performing page level classification for each of the elements in a page. We need this because when we're trying to work with language models, models are as good as the data is. So we are trying to get a cleaner data set here by eliminating elements such as headers, footers, page numbers. So that's why we augment this knowledge from the object detection methodology. We normalize the bounding box element and then get the extracted clean text for each of the EDD chapters. Moving on to classification. So the classification framework, as I showed in the data flow diagram, is capable of performing three kinds of classification. The single label classification is similar to a multi-class classification where it's choosing the best label from a set of predefined labels. The top three labels, so in this experiment, we generate the probabilities for all the labels possible. So this is a multi-label problem where the model is predicting the top three probabilities from a given set of labels. And the two-level label is an LLM augmented approach where we get a more granular level classification by prompting the LLM to generate labels at a much granular level. So not just categories, but also subcategories. So the first approach was to map the departments of our ETDs into the ProQuest label because we wanted to have a standardized academic label system. We then compare machine learning-based classifier with language model-based classifiers. We compared the pre-trained versus fine-tuned language models, generate the top three labels by modifying the activation function, and finally use LLMs for classification. For evaluation, we looked at F1 precision recall and accuracy, the common metrics used for classification, but we also looked at the receiver operator characteristic curves to kind of understand how the models are performing at different thresholds and to get a better idea of machine learning versus language model-based classification techniques. So in this first experiment, we are comparing machine learning with language model-based classifiers. For machine learning algorithms, we used random forest and SVM, and for the language model-based classifiers, we used BERT, SciBERT, and their fine-tuned version. From the F1 scores, we do see that SciBERT that had been fine-tuned with the ATD data performed the best in classification, and machine learning algorithms such as SVM had much poor score. This is a ROC curve, the receiver operator characteristic curve that I was talking about. We measure the area under the curve for SVM, random forest, and the best version of our language model-based classifier. This particular graph shows for multiple classes. And here we just see the area under the curve. We do see that for machine learning model, the area under the curve highest was 0.51, whereas for language model based classifiers, the area under the curve was much larger at 0.98. So in this experiment, we are comparing the fine-tuned with pre-trained classifiers on the ETDCL dataset. We do see that, again, consistent with the last set of F1 precision recall that I showed, the fine-tuned counterparts for all the language model-based classifier outperform their pre-trained counterparts. And thus, we realize that augmenting language models with data from your particular specialized corpus does help us with classification. Moving on to classification using large language models. So we heard a lot about large language models in this talk, and people were talking a lot about GPT, but I specifically for my research try to use all openly available models. This is Meta's Llama. So I have performed experiments using Llama 2 and Llama 3, zero shot, few shot, and instruction tuning. So in zero shot, you typically just ask the model to perform something without giving any examples. In few shot, you give examples of how you want the results to be, or even examples of each of the classes you are trying for classification, each of the classes you are trying to classify into. And for instruction tuning, it is a way of fine-tuning the model without actually fine-tuning, because you're asking the model to closely follow the instructions that is provided in the data. For Llama 2, I did zero shot, few shot, and instruction tuning. And for Llama 3, that was released, I think, April of this year, I did zero shot and few shot, and I'll discuss the results in the next slide. So with Llama 2 that was released last year, we first started with zero shot prompting. And from the results, we do see that the output is not specific. So if it is not following a specific format, post-processing the outputs and actually being able to evaluate them is extremely difficult. We don't know what heuristics it's following. So even with different kinds of prompts, Llama 2 wasn't able to really help us. With few shot prompting, Llama 2's maximum context window was 4096, and we had more than 28 subject categories. So giving a positive and negative example for each of those categories would it would exceed the context window. So that also wasn't the best possible solution when working with Llama 2. So that we moved on to using instruction tuning for Llama 2, and the figure on the top is the guidance of instruction tuning that we use. We had our documents and labels, but we also added instruction to each of those data points so that the model learns how it's supposed to act when it gets data for classification. If you look at the table on the bottom, we do see that the model responses are relatively better, where we were able to kind of use some heuristic method to parse out the results. And it was following the pattern of giving the categories in quotation. So we were able to kind of use regex to extract the classes that it was predicting. Moving on to Llama 3, we saw tremendous improvement with Llama 3, where if you see in the table on the right hand side, it was able to give you the category and subcategory very easily, and it was fairly simple to extract the results from extract the categories from the results that it outputted. But I added F1 precision recall scores for all the models, all the LLMs that we used. And we do see that Llama 3's few shot learning has the highest F1 score, but this is really low. Now, 54% F1 score is it's correct 50% of the time, which is not a very good result. So we went into investigating what is wrong, why isn't the LLMs performing well. So we did see that Llama was predicting 82 distinct classes where our input data set had 47. Now, when we went into seeing what are these 82 different classes, we did see uh, variation of some existing class as shown in the slide, like linguistic as linguistic sciences, but we also saw a merging of different disciplines into one category. So, for example, political science was often predicted as political science and international relations. Now, due to the nature of our collection being so specified and us not having subject matter expertise in all the possible academic disciplines, we cannot say this is correct without having an expert in the situation. So that's why evaluation with when using LLMs becomes a bit challenging based on the task at hand. And we did perform a small level of user studies. It was really small because it's voluntary based participation. So, but we did see some positive results, which we want to expand in the future to evaluate them further. For the multi-label classification approach, we use BERT-based methods and LLM-generated methods to get multiple labels because the idea is to generate categories for each of the chapters, but also to understand the interdisciplinarity of research that goes on between chapters. So we might have chapters from computer science talking about biology because computational biology is a thing. So we want to understand the interdisciplinarity. Hence, we wanted multiple labels and not just to map to one label. For the BERT-based approach, we use sigmoid activation function, which gives you the probabilities across different classes instead of softmax and taking the maximum of them. This gives you I stuck to the top three labels because we wanted to see what are the top three labels here, and this gives you an idea of what kind of uh, topics might be discussed in that chapter. And the second was using LLMs to generate subcategories, and the LLM was prompted to generate multiple categories. So when evaluating the top three predictions on language models, so we are doing a multi-label evaluation with a multi-class evaluation. Now we don't have ground truth at the multi-label level, so accuracy is the best metric because we are just trying to understand what fraction of the classes the model got correct when compared to the ground truth. And we did see that the fine-tuned Cybert and Cybert with ETDs had the highest accuracy of 91%. So basically, in the top three label, it always found the label that was associated with the ground truth, which is promising, but it would be better if we had a multi-label ground truth to compare against and get the proper F1 precision and recall. For the LLM generated subcategories, again, it was an open-ended generation task because we wanted to see what kind of labels and LLM was generating. And the table on the right-hand side kind of gives you an idea of what subcategory LLM outputted. Now, we again don't have any proper ground truth to evaluate this against. So we used a cosine similarity between the ground truth and the generated results because it's an open-ended generation. We wanted to see if there is semantic similarity. We did see that only 12.6% of the results had a similarity score of 0.6 or higher, indicating that there was limited alignment between the ground truth. Now, the concept of LLM is to understand hidden kind of intent in the text and give out results. So we did not expect direct alignments. This is kind of needs more evaluation to get a better understanding of how well the subcategories are aligned to the chapter text that's been introduced in it. So to conclude, language model-based classifiers such as BERT and Cybert did outperform traditional machine learning and SVM models. Fine-tuned versions of the models were better than their pre-trained counterparts. The multi-label approach did outperform the multi-class approach with the highest accuracy of 91. And experiments with Llama 2 and Llama 3 show that LLM can have greater insights from the data, but it is extremely challenging to evaluate without human intervention, and that is kind of costly in this context. So to conclude, our machine learning and AI-driven chapter-level approach can improve ETD discoverability and accessibility by providing users with more granular level data. And we have done some very small scale user study, which we are expanding to basically have more data where users have used our system and they verify that, yes, they found it easier to find their portion of interest. LLM-based methods show promise, but the generated outputs are not often constrained, making post-processing difficult. And the LLM predicted classes might not often lie in the ground truth, which again makes it difficult for us to evaluate if they were right. And finally, we are refining and optimizing our prompts and also incorporating a chain of thought reasoning approaches where we kind of go back and forth with the model. Why did you predict this? Would you change your answer if given a chance? So there has been studies which shows that it kind of, if you challenge the model, it kind of tries to think deeper, think. And also latest, like recent models such as 5.3, Llama 3.2, Mistral, these are models with longer context window with 120K plus context that is being supported and have shorter memory footprint. So like it's easier for us in an academic setting to use these models and get a better understanding of how they're performing. And again, human evaluation is needed to verify the usefulness of the granular metadata as well as to evaluate the LLM generated data. These are my references, and